Welcome to 1D Kinematics, solving multi-step acceleration problems. Okay, so we're going to just jump into it with an example. On a straight 1 kilometer track. Now, what is 1 kilometer? 1 kilometer. A kilometer is much larger than a meter. And so we know that 1 kilometer is 1,000 meters. Always check that. Okay. A race car accelerates from rest to its top speed. So it starts at rest to its top speed through 325. So that means it's constant acceleration, we believe. 325 meters west at 3.5 meters per second squared. So let's start with what we know so far. We know that we have a car. It starts from rest. It accelerates over 325 meters. And this is going to be west. I probably should have drawn it the other way because here we have, that would normally be east. So let's rearrange this to make it west. So you have a car. 325 meters. V1 is 0. We know that this is our top speed. And we know that the acceleration is going to be 3.5 meters per second squared. Then the car decelerates at a rate of 1.9 meters per second squared east to a complete stop. So let me shrink that down. So at this point here, that's its top speed. And now it's still going to be going this way, but it's slowing down till it finally stops right here. So our V3 is 0, okay? And here in this portion, we know our acceleration is negative 1.9 meters per second squared. Now here it's a little bit confusing because it says east, but what that means is instead of having a positive acceleration, which this over here is a positive acceleration, it means it's speeding up. Now it's slowing down here, okay? Okay, will the car stop before the track ends? Okay, so we know that the track is we know that it ends at 1,000 meters. So the question is, here we have 325, right? The question is, what is this distance, right? All right, so let's look at this. What's the strategy? First, draw a diagram of the situation. Use V1, V2, V3 for the 3 different velocities. Solve the problem in parts. V2 is the final velocity for part 1 and the initial velocity for part 2. Use V1 and V2 again with new values if using V2 and V3 is confusing. Solve for delta D and compare the sum of the 2 displacements to the 1 kilometer restriction. So we're going to first look at, well, they drew it the other direction. We're going to first look at the first section, which is just this, okay? So here, we know our V1, we know our acceleration, we also know our delta D, and we're solving for V2. So we can use this equation, we plug it in, our V1 is 0, so this goes to 0. And then we have 2 times our acceleration, which is 3.5, times our delta D. We solve that out, and we get V2 is plus or minus this number. Now we know that the acceleration is going to be in the positive direction, so it's going to be a positive V2. Okay, so now our V2 is this, but now we're looking at the second section. So now we say, okay, we know this V2, and what was the value of it? It was 47.69. Oopsie, I went too far. We know this is 47.69, repeating. So now we're looking at this section. And just to make sure that we don't mess up with our variables, we're going to relabel this now because this is going to be V1. And this over here is going to be V2. Okay, so we have V1 is 47.69, acceleration is negative 1.9 meters per second squared, and V2 is 0. And we don't know the distance. So now we have those, and we're going to solve for D. So we rearrange the problem to solve for D. We stick in the values. This is 0. The end value, V2, is 0. We multiply that out, and we get delta D equals 598.68. So if we add those two distances up, the delta D from the first, which is 325, and the delta D from the second section, we get a total of 923.68 meters west. And since the race car is 1,000 meters, yes, the race car will stop before the track ends. Okay, example 2. Just as the traffic light changes to green, a Mustang drives through the intersection at a constant velocity of 4.2 meters per second north. This is a constant velocity. A Camaro that was stopped at the light accelerates from rest at 2.9 meters per second squared north. So this is like a different car. It was stopped at the light. It accelerates from rest at 2.9 meters. How much time passes before the two cars meet again? How far have they traveled? Okay, so first, draw a diagram. Write your knowns and unknowns for each car. Delta T and delta T will be the same for both cars. Remove delta D by isolating it, rearrange, and let's just start with the diagram. Okay, so pause the video and see if you can do this on your own. Okay, so now we have two cars. The first car, the light turns green just as the car passes through the intersection. He's going a constant speed of 14.2 meters per second north. That's our car 1, okay? And then car 2, let's choose a different color, is over here. It's stopped. So its initial velocity is 0. It's accelerating at a constant rate, okay? And then over here, we don't know those. Okay, so we know that, but we do know that at some point in time, which will be the same delta D in the same time, they're gonna pass each other. They're gonna be passing, okay? Now, since this car started from rest, it'll be going faster than when it passes. But at a moment in time, they will be at the same place at the same time. So if we look at the two equations for our Mustang, and that's why we notice that we have, for the Mustang, we have an M variable. And for the Camaro, we have a variable of, we have the C variable down here for Camaro. Okay, so for our Mustang, we have its velocity is that, delta D, delta T, right? And it's at a constant velocity. And for the Camaro, we have initial velocity, constant acceleration, and we don't know those. So for when you have a constant velocity, we have delta D over delta T, right? And over here, the equation we can use over here, because we want delta D, we want two equations and two unknowns. So we have two unknowns, right? and we have two equations. So over here, we can use this equation. And notice that we have an equation over here that does not have, there's no V2 because we don't know what that is. Okay. So when you isolate delta D, and you can sub in, so here you could solve this for delta D. So here, oopsie, we could say we can multiply both sides by delta T, right? And so you would have delta D is equal to Vm delta T, right? Which is right down here. Okay. Then once you have that, you can take this equation right down here and you can put it into here. So we have Vm delta T, which is what we said, is equal to all of this. And we know that the initial velocity of the Camaro is 0, so we can get rid of that. And that simplifies the problem quite a bit. So Vm delta T equals 1/2 A delta T squared. So you can move this over to this side, and you get 0 is equal to 1/2, all that. And then what you can do is you can put in the numbers. 1/2 times 2.9 times delta T squared minus 14.2 times delta T. You can take out 1 delta T. And then so we know that delta T can be 0, right? So you can basically either this equals 0 or this equals 0. Because 0 times a number equals 0, or a number times 0 equals 0. So one of those would have to be 0. And we know that delta T isn't 0, so we can eliminate this from it, and we can just solve for this. So 0 equals 1.55 delta T minus 14.2, and then you solve for delta T, and you get 9.79. Okay? So this is when they first met at 0 seconds, and this is when they met again at 9.79. Now this problem is actually much more difficult than the typical problems that I give my regular physics classes. Okay, so now that you have your delta T, you can plug this in either equation, but this would probably be the easier equation. But you can plug that into either equation to solve for the answer. So if we plug in delta T into here, we can get our delta D is equal to 139.06 meters. So the cars meet again after 9.8 seconds and 140 meters north. Here's another example. Two hockey players are skating towards each other. They are 50 meters apart. The first is accelerating from rest at 0.74 meters per second squared, and the second has already attained his maximum speed of 6.2 meters per second. Find how long before they hit each other, how fast was the accelerating player going at this time of contact, and how far has each player skated. Pause the video and see how far you can get. And then, okay, so we start off by drawing a diagram. We write out the variables for both players in their own columns. We make a connection between the displacements and the 50-meter restriction. We choose an equation for each, isolate to eliminate delta D, substitute, and solve. So let's look back at the equation. We have two hockey players are skating towards each other. So we have like one player over here, one player over here, and they're skating towards each other, right? They're 50 meters apart. The first is accelerating from rest. So let's give them names, like B Bob 1 is 0. Let me change this to, so the first is accelerating from rest. So from rest, and its acceleration is this. And the second player, let's use a different color. has already attained its maximum speed. So the second player is moving at 6.2 meters per second. And it's moving at a constant, so it's not accelerating. Okay? So let's go ahead here. They drew a much nicer picture than I did. So we have this initial velocity here. We have its acceleration. This one's moving at a constant. We have delta D. Those are different, but we know that they add up to 50 meters. So what do we know? We know this. We know this. And they have A and B. We can say Adam and Bob. Okay, so this is player A, this is player B. B, we know all this. We know that delta dB will be negative, okay? And we also know that delta dB, we can say that we know that delta dA plus delta dB equals 50. So we can solve for delta dB here and say that delta dB is negative 50 plus delta dA. Okay. Alrighty. Imagine this player moves negative 50 meters all the way to player A, plus whatever player A moves. Okay. So, solution. Part A. We need to find an equation that has delta dA, because we have dA and delta t. So here, this has dA, VA1, which we have, and it's delta t, it has acceleration, which we have, and that. So the two unknowns is this and the delta t's, and we know the other two. For player B, we use our average velocity equation, which is this, okay? And we know this, and we don't know, these are our unknowns. So again, we have the same, okay? We can rearrange to solve for dB. We put this into our dB equation, because remember, we're using this equation here, okay, and we're moving this all the way down to here, okay? So we substituted it to here to get this. So now we have VB delta T equals negative 50 plus delta dA, and we can, excuse me, and we solve for delta dA. Okay, now that we have that, we can substitute this in for our delta A, delta dA right here. Okay, and then we have this equation is equal to this equation. So we have 50 meters plus VB delta D, this right here, which is right here, equal to this right here, VA1 delta T, right there. See this? Okay? And we know that the initial velocity of player A is 0, so we can eliminate this term. Now we can, it's a little bit simpler without that term, and now we plug in everything that we know. We know that the constant velocity B is negative 6.2. We know our acceleration of A is this, and our unknowns are the delta t's. So now we multiply it out, and here we end up with a quadratic. So 0 equals 3.37 delta t squared plus 6.2. Then we use our quadratic equation to do that, and delta t equals 5.95 delta, which means, so there's two possible solutions for this equation. The first option is 5.9. The second option is negative 22.7. You can never have a negative time, so therefore the correct answer is the 5.95 seconds. So if we look at if we go back to our thing, we know that the time at which they hit right here, delta t, is going to be 5.95 seconds. And it's going to be the same, right, for both players. Okay. Then I think it's asking for other things. So here, we just solve for this. How long before each player hit? Now, the next thing we're going to solve for is how fast was the accelerating player going at the time of contact? So now we're looking for this. So now if we go to here, we want to know, and now we're looking at this guy, player A, because he's the one accelerating. And now it wants to know what VA2 is. That's the question. So now it's a little bit easier. We have our delta t, we have our VA1, we have our acceleration. So we can solve using those things. So here's our equation, VA2 equals VA1 plus A delta t. We plug in the numbers that we know, and we get VA2 is 4.403 meters per second. Okay? So now we know this is 4.4 meters per second. And so now the last part is how far has each player skated? So now we want to know how far they've skated. So we want to know delta D A, and we want to know delta D B. So here, delta dB, we know that VB is delta dB over delta T, which if you arrange, looks like this. We can plug in our values. We know it's 5.95 seconds. We know the constant velocity is that, and we get our value to be negative 36.89. Okay. We can plug that into here. We can put that value into here because this is our second equation, right? We know that they add up to 50. So when you do that, you know that delta dA is 13.11. So those are our two answers. The displacement of B is negative 36.89 and the displacement of A is 13.11. So the players meet at 6 seconds later. Player A has a final speed of 4.4 meters per second and traveled 13 meters, where player B traveled 37 meters. Tips for solving multi-step acceleration problems. You draw and label a diagram, write down the variables separately for each object, have separate columns for each object. The number of equations needed depends on how many unknown values there are in the problem. If there are 2 unknown values, 2 equations are needed. Tips for solving multiple. Okay, time is a useful variable to solve for. It is often equal for 2 different times. Displacement may not be the same for both objects. Consider the direction of the displacement for each object. To help you write an equation that connections displacement, consider the displacement of each object if the other was not moving. And make sure that also with the displacement that you establish a plus, a positive, and a negative direction. Hockey player's example. Hockey player A was accelerating from rest, moving in a positive direction towards player B, who is 50 meters away. From hockey player A's point of view, A will travel plus 50 meters if player B is stationary. Player A will travel plus 50 meters, plus whatever displacement player B has, which is negative, right? From hockey player B's point of view, B will travel negative 50 meters if player A is stationary. Player B will travel negative 50 meters plus whatever displacement player A has. And when we say plus, we say player B will travel plus. When we say plus, it actually is subtracting because player A is moving in the opposite direction. So we can add a different direction to it and it becomes less. Okay, so in the case of this, we add a negative number and this will become less. In the case of this, we're adding a positive number, and then the delta dB value will become less, a lower magnitude. When using equation 3 to solve for time, identify the method for solving. Okay. So here, if like, and when you have like things like this, almost like quadratics, it just gives you some tips on how to do. Like you can do common factoring like we did in the first example. You can do rearranging, and here you're going to take the square root. And then here if you have, you know, basically this is like quadratic example where you have it a squared, a to the 1 power and to the 0 power, because here there's no delta t, so it would be delta t to the 0 power, which is 1. Okay. I know that was challenging. Like I said, these are probably more difficult kinds of problems we do. Let me know if you have any questions.